In this video, I'll solve a problem using torque for a yo-yo that is in equilibrium. So this is a static equilibrium problem. So here I've drawn the situation and I've written out our knowns and unknowns. So the only things we're actually given is the mass of the yo-yo. I called that capital M. So this thing has a mass 0.101 kilograms, and we know there are two R's, and the one that's labeled big R here is 5.6 times larger than the one labeled little r, but we don't know what either of them actually is. And we're supposed to find tension 1, that is this string that is holding the yo-yo from the top, and tension 2, which is in this string, which is on the outer part of the yo-yo and holding a small mass. We're also supposed to find how large this mass is. So it has to be a mass that's just big enough that it can keep this yo-yo in static equilibrium. So static equilibrium, that means net force is 0 and net torque is 0. So if I do a free body diagram of this mass, net force, let's see, we've got mg going down, we've got T2 going up, and if the net force is 0, that tells me that T2 equals mg. Alright, so that would give us T2 if we knew what m was. Let's try something else. Free body diagram of this whole thing. So net force on this thing, tension, T1, and then gravitational force. So mg here, and then the big M, g there. So in order for the net force on that system to be 0, T1 has to equal little m plus big M times g. So again, we could find out what T1 is if we knew what little m was. So that's as far as we can get with net force. Now we've got to look at net torque. So we have to decide on a pivot point. With a static equilibrium problem, you can actually choose any pivot point. Nothing's actually moving. So any pivot point works. It's best to choose one where you know all the distances, and sometimes it's also good if you choose one where there's a force that you don't care about. In this case, the center of the yo-yo is a good pivot point because we know little r distance and big R distance that go to the forces, two of the forces we're looking for, T1 and T2. So let's try that one. So we'll use the center as the pivot point. So the net torque around that point, we have T1. So T1 is pulling up this way. So the direction T1 is trying to make it turn is this direction. So that's the positive direction. So plus T1, that's the force, times the distance, little r, times sine of theta. And theta is right there. It's 90 degrees, so that would be 1. So T1 times r, and then we've also got T2 out here. So on the yo-yo, T2 is pulling down. So we've got T2 at a distance, big R. And if it's pulling down on the yo-yo, then that's trying to make the yo-yo turn this direction. The negative direction, clockwise. And the net torque has to be 0. So this means that T1 times little r equals T2 times big R. So now what can we do with this? We can try putting these in. So T1 is little m plus big M times G times R now equals T2, which is mg times big R. So the G's go away. All right. And we know that big R is 5.6 times little r. So m plus little m plus big M times little r is m times 5.6 little r. Now the little r's go away. If we subtract the one little m from each side, then we get big M equals 4.6 little m. And we know big M. So now we can find little m. 0.022 kilograms. All right, now since we have little m, we can come back up here and find T2. So T2 is 0.022 kilograms times 9.8 meters per second squared. And then T1 is 0.022 kilograms plus 0.101 kilograms times 9.8 meters per second squared.